Math 1314, Tyler Junior College, section 4.3, properties of logarithms, change of base property, examples and observations. For those of you watching strictly for college algebra reasons, the first two examples will suffice. But for those of you who want to make your brain work better, and for those of you going into more advanced math classes, I strongly recommend watching the last two examples as well. The first two are just what we did in the previous video. Approximate a logarithm to 4 decimal places. Log base 7 of 91. Log base 23 of 529. We can use the change of base property to rewrite both of them as a ratio of logs using any base that I want. If the objective is to use a calculator, then you want that base to be either 10 or e. For example, I invite you to pause the video and try to work these two, but I'm jumping into them right now. If we wanted to evaluate log base 7 of 91, all we have to do is set up a ratio of logarithms using any base we want. I'm going to use base e, which means I'm going to use natural logarithms. Just remember, the original argument is the argument of the logarithm in the numerator. The original base is the argument of the logarithm in the denominator. You can put that in a calculator. But I want to remind you that the choice of base is arbitrary. Had you used base 10, you would have had the exact same expression, but it would have said log instead of ln. Don't believe me? Get out your calculator, put in one, get out your calculator, put in the other. I'll do it. All right, for the first one, we need to type in 91 and press ln, which is, wait, this is in the same calculator I had before. Oh, it's over here. Oh, this is a display calculator. All right, for a display calculator, you type it in the order you see it. So ln, notice it defaulted open parentheses, 91, close parentheses, divided by ln 7, close parentheses, equals about 2.3181. Had I used log 91, close parentheses, divided by log 7, close parentheses. Exact same answer, 2.3181. It doesn't matter what base you choose. Just choose one. But if you're going to use a calculator, you should probably choose base 10 and use the log button, or base e and use the ln button. But regardless, it's approximately 2.3181. How about the second one? Really, it's just like the first one, just different numbers. I'll just use ln. Natural log of 529 divided by the natural log of 23. I'm not going to go back to the screen. You saw me do it once, you can see me do it again. It looked exactly the same, just different numbers. But this one might surprise you, because the answer is not approximately anything. The answer is exactly 2. Wait. That's the answer to this question, and remember that this question is what power turns the base into the argument. Well, according to this, that power is 2. Oh, you didn't know 23 to the second power was 529? I did. But had you known that in advance, you could look at it and go, oh, it's just 2. Because I know the question it's asking, what power turns the base into the argument. But it's okay if you didn't know it, because the change of base property still gets the job done. For those of you just waiting for college algebra material, you can stop it now. For those of you that want to be better math people in general, better students, smarter people, or you're going to take more math, hang around for a little bit longer. Oh, here's the other calculator. Use the change of base property with base 2 to evaluate without a calculator. Log base 8 of 32. Now, why do you think I said base 2? You notice something about the numbers 8 and 32 that they have in common? Well, let's set up the change of base property using base 2. Log base 2. Original argument is the argument in the numerator, so 32. Original base is the argument in the denominator, so 8. Do you see why using base 2 is a slick move here? Because I know the answers to both of these questions. Remember, a log's like a question. The question in the denominator is what power turns 2 into 8, and hopefully by now you remember that 2 to the 3rd power is 8. I'll just put a reminder, because 2 to the 3rd power is 8. But do you know what power turns 2 into 32? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. It's 2 to the 5th power. Because log base 2 of 32 is 5, because 2 to the 5th power is 32. Okay, so the answer is a rational number. Big deal. What's the point of this example? Well, the point of this example is if you notice something, maybe you can take advantage of it. If you had noticed that both the base and the argument were powers of a new base, in this case they were both powers of 2, then we could rewrite the logarithm as a ratio of logs with base 2, and therefore answer both logs. But can we go further than that and make a generalization? In other words, can we figure out what structurally made this work so nicely and capture that structure with variables instead of specific numbers? And the answer is of course. Otherwise I wouldn't have taken us down this path. I'm going to back this equation up and put one more log to the left of it. Now I'm still going to write 32 in the argument, and I'm still going to write 8 for the base, but I'm not going to write them as 32 or 8. I'm going to write the 32 as 2 to the 5th. And guess what I'm going to write the base as? Not as 8, but as 2 to the 3rd. Now it looks kind of weird and awkward to have a base that's written as an exponent, but if you can tolerate the multiple tiers of numbers, this still says log base 8 of 32. But by rewriting both the base and the arguments as powers of the same base, take a look at where this problem now begins, and take a look at where it ends. Now, can you make the generalization? Remember, to make a generalization, you write down how it begins and how it ends, except you take out the specific numbers and you replace them with variables in an effort to preserve the structure of what's going on. So how would we do that? Well, we would have to start by writing this with no numbers and preserve what's so special about it. And what's so special about it is that the argument and the base of the logarithm can be rewritten as powers of the same base. How can I write that over here? Well, let's start by writing the argument as b to the x power. How can I write the base? Well, it's got to be a power of the same base b, but the exponent might be different, so we'll say b to the y. So instead of 2 to the 3rd for the base and 2 to the 5th for the argument, we'll say b to the y power for the base, b to the x power for the argument. Okay, what are we conjecturing this equals? Well, what's the quickest way to get from this answer, this problem to this answer? It's just the ratio of the exponents, isn't it? So if I did that over here, what's the ratio of the exponents, x over y? Now be careful, this is a conjecture. It has not been proven yet, but it would be pretty easy to prove. Just use the change of base property on this using base b. I challenge you to try it, it's not that hard to do. So for those of you aspiring to be future mathematicians, this is what a lot of us do. We look for patterns, we make conjectures, and we test them. Speaking of patterns and testing, now this one's kind of set up a little bit more Instead of giving you two specific logs, I gave you two generic logs. What is the relationship between log base b of a and log base a of b? If they're all permissible bases, so everything's positive but not equal to 1. It may not be obvious what the relationship between those two are. And in fact, I want to clear the board and move this up so I have some room underneath it. But to explore the relationship between two logarithms, where the only difference is the base of one is the argument of the other. That's the structure I'm identifying here. The base of one is the argument of the other. Is there a relationship between their answers? You know, this is so pretty, I hate to erase it. Don't worry, I can figure it out again if I had to. So what's the relationship between log base b of a and log base a of b? Well, let's start by taking the first one, log base b of a, and applying a change of base property to it. Well, why don't we just write exactly what it says? It's a ratio of logarithms. Actually, I'm not going to write exactly what it says. It says we can do this for any base we want. Why don't we use base 10? Original argument is the argument of the numerator. Original base is the argument of the denominator. What would happen if we did that to the other one? Log base a of b. We get almost the same thing except the complete opposite. And when I say complete opposite, I mean the reciprocal. If we use log base 10 again, and by the way, I can use a specific base here because the generalization I'm attempting to make is with these things, not with what base I choose to make. If I apply the change of base property to this, and this is where you really have to focus on the structure of a property, not the letters in it. The original argument is the argument of the numerator. So the original argument is the argument of the numerator. The numerator is log of b. The original base is the argument of the denominator. So the denominator is log of a. What's the relationship between these two ratios of logarithms? They're reciprocals. So how can we capture that generally? Well, generally the reciprocal of something is 1 over it, such as the reciprocal of 2 is 1 over 2, the reciprocal of 7 is 1 over 7, the reciprocal of 9/13 is 1 over 9/13. Oh, that doesn't look right. What if we multiply both sides of this by 13? We get 13/9. Oh yeah, that looks like the reciprocal. So in general, to represent the reciprocal of something, you can just say 1 over it. So I think we're ready to make a generalization. One of these is the reciprocal of the other. It doesn't matter which one we start with. Therefore, let's start with log base b of a and say that it is the reciprocal of log base a of b. So it looks like if we switch the argument and base in a logarithm, the answer gets reciprocated. I like theoretical things like this. People ask me, what's that good for? Who uses this? And as a theoretical mathematician, my reply is, I really don't care. Theoretical mathematicians do math for the sake of doing math. Applied mathematicians do math for the sake of accomplishing another goal. Think of it as climbing a mountain. Some people climb a mountain because it's there. That would be the theoretical mathematician. Some people climb the mountain because they need to get to the other side of it. That would be the applied mathematician. All right, that wraps up this video series for section 4.3. I hope you learned something. Hope you enjoyed some of the theoretical discussions we had.